we have some numerical example. So for example, you are asked to design an LNA at frequency of 5.5 gigahertz, and then the VDD equal 1 volt. Again, is the Cascode common gate, common source amplifier with inductive biasing, right? Remember, if I say this few words, are you able to draw the circuit? It is common source with inductive biasing, right? So this is the V in, and it's Cascode, so I know it is this. And then inductive biasing also as the loading. You have parasitic resistor and capacitor, right? I need to bias it, and I remember last time I decided to bias the Cascode transistor at VDD. And in order to bias the this one, I actually use a diode connector device. But this is not accurate because I need to give a current source. And then I have a cap just for the noise. It's a bad drawing, but are you able to follow me? I don't have it in my cheat sheet, but let's take a look. We have this here, right? That's exactly what I'm drawing. This is a common source. No, common gate. I say the wrong thing. This is common gate, not common. VL is here, yeah? Common gate, right? Oh, I make one mistake already. I keep saying that is common source. Common gate, of course. I put the gate at constant, right? So this is called VB, not VS in the other slide. But I just want to show you that if you understand all the keywords, see, I also can draw it without a cheat sheet, right? Cascode, and then reference. I also put, yeah, it's correct. I put it at the right place, although I draw it directly to the VDD. And when we say the frequency is at 5.5 gigahertz, it means at 5.5 gigahertz, you want this tank to resonate. You want this to resonate, right? Both of them become open circuit. Okay, so what did we say last time? The first thing, we find the peak. What should be this one? So last time we say we want to find the peak GM when you change the ID, but then that is too power consume too much power. We only will take about 80% of it. So this is about 12. 80% may be about in the order, let's say it's about 10, right? They give us about 2. So here we get ID0 equals to 2 milliampere. I want to bias it with 2 milliampere, and it gives me 10 millisiemens of transconductance. Now 10 millisiemens is what? Is 1 over 0.01 equal to 100 ohm, right? But I want 50 ohm. So I need to double the width equals to 20 micrometer, and I equal to 4 milliampere, so that I will get the GM equals to 20 millisiemens, which give me 50 ohm. 1 over GM equals to 50 ohm. Is this okay? Any questions? Yeah, you need to do a simulation for this. Yeah, DC. These are the DC biasing, right? No, they have nothing to do with RF, right? You just have a single transistor. So you don't build the circuit yet. You do a single transistor, sweep the ID, and then extract the GM, plot it. You see what I mean? To under the property of the transistor. And you need to start with some example. I think just use this example. We are also 65 nanometer, right? And it won't be, the number won't be the same. The point is that you tell me that you extract a certain GM, 80% of the maximum, and then you scale it to give it 50 ohm. And again, because it's Cascode, so this is pretty okay, right? If you are not Cascode, if there's channel length modulation, and actually you have a lot of channel length modulation because we are using minimum size transistor. Okay, so this is the first step, right? So we are going to use 4 milliampere and then 20 micro, right? So now this is done, 20 micrometer. But how do we bias it so that it's 4 milliampere? We do it step by step. The next one is LB. Again, what is the purpose of the LB? LB is that I need it to do biasing, right? This is not correct, right? If you really draw the circuit, there should be a coupling capacitor, right? You cannot connect your input directly to it. Otherwise, you will short it. But as we said last time, your LB is there for biasing, but we also want to resonate it out, right? We have other parasitic capacitors. So here is just, it is given. But for you, you can do that from simulation. This is for this example. CGS equal to 30 femtofarad. Okay? You can get from simulation. You DC bias the transistor, then you can see the property. It will give you all the CGS, CDS, everything, GM, out. You get from there. Right, so CGS equal to 30 femtofarad, and CPAT in this case equals to 50 femtofarad. I gave you in the project already. You just use those values, okay? But you need to tweak a little bit, right? So omega equals to 1 over square root LC. And now we are talking about 5.5 gigahertz. So this is 2 times 3.14, 2 pi. Times 5.5 times 10 to the power 9, right? Equals to 1 over square root 80 femto. What is femto? 10 to the power what? Negative what? 50. 10 to the power negative 50, right? And then times LB. So from here, then you just do the math. It say that LB equals to 10 nanohenry, pretty large. Okay, now if you put 10 nanohenry after post layout simulation, this one is going to introduce new capacitor, CL, right? Because you lay it out, then you have a pad, right? Then you need to iterate to make it. Like it introduced CL, then it increased the C, iterate, so that 1 over square root L C equals to omega. That's what I want to say. Do you understand what I mean by iterate? Iterating, right? So then done. I have the LB. I still not doing the circuit yet. I do it one by one. And now the bias circuit. Like we don't have much time. If I were you, I just follow what is given in the suggestion, right? We say that for biasing circuit, don't need to consume too much power. This guy is already taking 4 milliampere. I need to bias it with a certain current. And last time I said maybe just take 1/4 of it. So maybe, how about, let's take 1 milliampere. Yeah, so you can just put 1 milliampere there as the reference. But then you need to, this is a current mirror. As I said last time, your current 1 milliampere is going to be converted to the voltage. And this voltage is going to apply to M1. And in order to have 1/4 ratio, then you are going to have WB equal 1/4 times W1, which is equal to 5 micron. Because earlier we say that we choose W equal to 20, right? So this one, if you put 5, if everything works out, you will get 1 milliampere for 4 milliampere, but you won't because of channel length modulation again. So that is okay. If I were you, I would just I think it will get too large. So you will just reduce the width of WB a little bit. It's not a big deal, right? Instead of 5, you just keep changing it so that this one is 4, right? Or if you really want, how about just make the current source to be smaller, right? No one asks you that, mandate you that you need to be 1 milliampere, right? The goal is whatever came out from your calculation. Now, you might not get 4 milliampere. Remember, this is the technology the textbook use. We're using cadence, right? They have different. So it might not be 4. If you cannot get what you want, I will just change the width of this guy. As long as it's not too much difference, right? If too much, then you need to think carefully because it might actually, the whole thing is wrong, then you might bring the other parts into saturation because of the headroom issue. For example, if you make this one too high, you might drive this into linear mode. Okay? Yeah, so just be careful. Always try to check if you are already, when you start doing simulation, right? In your calculation, of course, you make sure it is in saturation. But once you do simulation, all this channeling modulation or some secondary effect can bring you into linear. And whenever you see, it doesn't make sense, my hand calculation shows this should be that, but why it is not the case? For example, you think that this one should be about 1 to 4. Even there's channeling for modulation, it should not be 1 to 10. So either you put something wrong or this one was in linear mode already. That's why you don't have current mirror effect, right? So remind yourself about this. And this one is not that important, but if you have time, go deeper to study what CB should be, this filtering capacitor, right? You start with 1 picofarad maybe. This is to filter the noise, right? If it's too large, of course, your area is going to be too large, which is not good, right? But too small, you don't have the effect. So any questions? Now, if no, then we are done with this. And then how do we choose M2? So as I said last time, start with M2 equal to M1, right? You are going to change it as you simulate. But remember, this happened to me also. I'm not experienced. When I change it, very often I keep changing and everything looks okay. I already brought M2 into linear mode. This is a mistake I always make, right? So you also be careful when you're trying to change, when you are changing it, right? So I will start with this, and then you have the freedom to change it wider or narrower, but don't be too much. Once it's too much, you will go to linear mode or the transistor becomes too much. The capacitance becomes very dominating, and then maybe you match the currents, match the GM, but then you cannot resonance. You need to change the L1 again. So they just keep have the same. I mean, they just affecting each other, right? So this is M2. Now, how about for the output cap? Output cap I gave you already, right, in the handout. But in this textbook example, you just said the total output cap. We assume we already know that. In the project, you need to just do a simple addition. It's 75 femtofarad, okay, which is the loading plus the CDG2, right? And that is where I said that if you make your width too large, then your cap is going to be too large, right? And again, your goal is to what? Get into resonance. So it is 2 pi, or I just use omega. You want omega, which is 2 pi 5.5 gigahertz equals to 1 over square root C total times L1. Okay, here I need to emphasize C total, of course, also include the C1, right? Where C1 is the, maybe let me just say iteratively. This one, when you have L1, then you introduce C1. C1 is the parasitic capacitance of the inductor, right? This is also a large one, right? Here, give me L1 equal to 10 nanohenry also in this example. Again, you will iterate one more time to make it nicer, right? Doesn't need to be exact. Yeah, okay. Any questions? Right, so we are done with all of this. We know what's LB, biasing transistor, M1, the amplifying transistor, Cascode transistor, L1. And L1, remember, please use this model, L1 and LB. Turn on this model in your simulation. And with that, this is what the textbooks say, right? Take a look at this, maybe you will understand better. I do have this, for example, this is LB. The whole LB, you have the inductance, series resistance, parallel resistance, and parasitic capacitance, right? You only know this parasitic after you have done the layout. This you already know. Let me see. Yeah, and also depends on what type of inductor you use. And this is the pad. Yep. Now, the last thing that we care about is the gain. If this one and this one resonance, right? The 30 femtofarad, this is the loading. This is the C load, right? And this is the CL. This, maybe I would say this is 0 plus C GD2, right? Everything is a real one because as you asked, right? This is the output. Output is to drive the next stage. Don't like in a cell phone. Maybe I did not give you the context. This input is from the antenna. If you're talking about the cell phone, right? And you have low noise amplifier. Then the next stage, maybe you go to the mixer or whatever, right? So this is the output. Now, if they resonance, then what it means? It means, right? If resonance, or just right at the operation frequency, right, 5.5 gigahertz, then the load is just 6.9 kilo ohm, right? Because this is the parasitic resistance of the inductor. Once in resonance, you have 60.9 giga ohm, right? Kilo ohm, right? What is the gain? We know the gain, you probably forgot the number. It is R1 divided by 2RS, which is 6.9 kilo divided by 2 times 50. What is the gain? It's about 60, right? No, yeah, 60. 69. Okay, which is too large. We don't want that for the low noise amplifier. One reason is because when you have large gain, you have run into distortion. Now, this is something we did not study. All this supposed to work in small signal, but of course we want to increase the power, increase the range. When your gain is too large, you will run into distortion. It won't be linear. You might think this is not a problem, but no. Distortion means that you have higher harmonics because any curve can be approximated as the harmonics of it, right? 5.5 gigahertz and then 11 gigahertz, and then you keep going up. And all this eventually, when you go through the circuit, their gain have a larger slope when the power increase. Eventually, they will take over the tone, the bass tone. If you look at the gain or output power as an input power, for the first harmonic, you may have something this. For the, not first, I mean for the bass tone, right, or first harmonic, right? And then if you go to third harmonic, it has deeper slope. Now, when your power is low, this is in log scale. You can ignore it. But once you reach a certain power, it becomes larger than your original frequency power, right? So there's something called 1D, what? I forgot the name. Anyway, What do you remember? One IP3, what's that? Yeah, compression point. Yeah. Oh no, that's compression. Is that the lean? Yeah, the I'm not just talking about IP3, the interception, third harmonic interception. Compression point is that when you go to high enough power, the gain drop, right? Here I'm saying that the third harmonic actually has larger slope. When you go to higher power, it will cut the lower frequency one. Yeah, but compression point is also another thing, right? So that is just one reason, right? And many other reasons. Now, so what do we do? So we add this RD. RD equals to 1 kilo ohm. Because it is small, RD parallel R1 is approximately equal to RD, right? Very large parallel, very small. The small one will dominate, right? So then what is the gain now? Now the gain is, of course, this is negative, but I just put it as positive. The gain is what? RD is what? Now it's 1 kilo divided by 100. Then I will get a gain of 10. Okay, just an example. What is this in dB? Let's go through the equation. This is voltage gain, right? How do you find dB? Equals to 20 log 10. Okay, if it's voltage, you 20 log. If it's power already, you 10 log. Okay, remember this. You need to memorize this. So this is 20 dB. So this, is that right, 20 dB? Yeah, 20 dB. And why mine is not? Yeah, that's correct. Okay. Any questions? So I say 5 minutes again. I spent half hours on this, but I think this is useful. I really hope that you can follow this to come up with your first version, and try some time to optimize it. I'm not asking for too much, but I want you to clearly document what you have done. You know what you need to do at least, and then repeat this for 77 Kelvin. You may say there's problem in the model or whatever, right? And then that would be good enough, right? Try to optimize it. Although last time I told another student you cannot use another architecture for fair comparison, but I try not to compare your number unless your number is really bad, showing that you are not studying, not trying hard, right? So if one of you get 4 dB noise figure and another gets 6 dB, maybe I won't care that much. But as long as both of you show me that you go through the thought process or tell me that why yours is bad, and you have both the room temperature and cryogenic temperature reasonable, right? You don't give me a higher noise figure at 77 Kelvin without explanation. Okay, good. So, and then this is what you need to plot. Again, there's a tutorial from Cadence, right? I want you to read, and you can plot the noise figure, gain, S11 gain is actually just S21, okay, in the scattering matrix. Okay, and then you need to match, you plot this to show me how you match the input impedance. For example, this one is 60 ohm, does not match well, it should be 50, right? Now, it's difficult. As long as you try your effort to show that at the 5.5 gigahertz, you have small imaginary part and above 50 ohm real part, I'm okay. But try to tune it a little bit, right? Do not give me 50 ohm imaginary part and 20 ohm real part. It means you have not tried anything. Okay? Yeah. Question?
I just want to ask, so we make the when we run it at 77, should we change anything or just
You do. You need to change everything. You need to start from scratch. Because think about GM. It is already different at 77 Kelvin, right? So you cannot have the same bias to get the same GM. But however, because you're supposed to have built your equation in a worksheet already, so you just need to enter the number, rerun it. So after you've done the 300 Kelvin, 77 Kelvin, since I do not push you to improve a lot, should be quick. Maybe 2 hours, within 2 hours you can get it. You cannot have the same layout because your transistor width will be different. Yeah, but this is only 3 transistors, right? And now, but in principle, you can do this. You can, after have the layout, then you just change the size. It should update. Now, if you're serious, they should have different layout because you change the size, the routing will be different to minimize the parasitic, right? But again, I am not trying to force you to do this. If you have a rather lousy layout, maybe I'm still okay. But do not have the metal wire going around the world and then come back, right? At least you need to make it closer, a little bit closer. But I'm not checking what, say, oh, this should go with a minimum distance, or your wire is not wide enough, so you have a large resistance. Then I'm not going to do that. But just make a reasonable effort. And the more important thing is that I want to see your thinking process while you do that, right? You can even tell me that this one doesn't work well because I was lazy. I have a very thin wire. I just don't want to enlarge it. Of course, I will deduct some point, but I'm not going to say, oh, this is the end of the world. Because the purpose of this project is to ask you to think through the design process. But I still want you to do some layout. But I'm not trying to force you to be trained to be a very good layout designer, right? But you know that it's going to hurt you if you don't learn it and you're planning to find a job related to layout in RF, right? Okay, so let's go to another topic related to